Hello everyone and welcome. So let's start off with a couple things here. Let's take a look at a couple problems, something like this here. We want to determine a couple things about the triangle, so let's go ahead and take care of this here. So the first thing to note here is that this, you can see this is a right triangle here for two reasons. One, you have the sine, cosine, and tangent, and also you note that it satisfies the Pythagorean theorem. 8, 15, 17 is a triple. So we can go ahead and sketch this triangle here. And then we know 17 is the biggest, so that means we know ST is the hypotenuse, that's going to be 17. So RS is 8 and RT is 15. So now we know that we're looking at S and T here. So we're going to go ahead and set this one up here and see what we can come up with here. So with angle T, right? So we can find sine of S, we can find cosine of S, and we can find tangent of S here. Now, again, you may recall, if you don't recall this here, go ahead and take a look at the definitions again. But we note here that we have our things. So remember that sine is opposite over hypotenuse here. So in this case for angle S, opposite the 15 over 17 here. So we can write this as 15 over 17. The cosine is the adjacent over hypotenuse, which is 8 over 17. And the tangent of S here, in this case, as you can see, the tangent of S is opposite over adjacent. The tangent of S here is 15 over 8, right? And we can do the same thing for the other pieces here as well. So let's go ahead and do that for the other pieces. So we can say sine of t, we can say cosine of t, we can say tangent of t. So by the same token here, opposite over hypotenuse, but now this time we're at this angle here, so be kind of careful about that. So in this situation, sine of t, in this case here, sine of t opposite over hypotenuse is 8 over 17. Cosine of t is 15 over 17, and then we should have tangent of t is opposite over adjacent, which is 8 over 15. Okay, so now we can take a look at a couple things about this here. So the first thing you may note to yourself is, wait a minute. So first off, we seem to have a sort of a linking here, right? These numbers seem to match. We got two 15 over 17s here. We got two 8 over 17s here. Furthermore, we have a 15 over 8 and an 8 over 15 here. So that's going to be an important thing. So you can kind of see this sort of thing is going on here. Now, the first thing you may note here is that, wait a minute, these two things here are the same, that the sine of S and cosine of t are the same, and the cosine of S and the sine of t are the same here. Now, if you take a look at S and t here, well, it makes a lot of sense because the way that this thing is set up here. For instance, in this triangle here, right, angle S, opposite S is TR, but notice that side is also adjacent to angle T here. So what was opposite angle S is adjacent to angle T here, and vice versa here, right? What is opposite angle T, in this case SR is 8, is adjacent to the angle S here. So we can kind of see that sort of thing. Now, that really only occurs, well, in this situation here, this only occurs in this sort of triangle here. So note that that means it has something to do with the fact that we're in a right triangle here. Now, if this is a right triangle, what do we know about S and T? Well, those angles have to sum to 90 degrees here, so that tells us something very important here. So notice how we seem to have this sort of thing here, so that we have the sine of S, or sine of A, and the cosine of B, right? These two things here. These two things are equal, and that seems to be linked to the fact that that we have ourselves a right triangle here. In this case, that A and B are complementary. So we seem to have this sort of setup here, where you have this sort of thing where as long as you have two angles that are complementary to one another, the sine of one is going to be equal to the cosine of the other. And this is going to be termed to be very useful to us here. So this allows us to conclude a couple of things based on this here. So I'll kind of explain how this works here, but you can kind of go through this thing here again and explain it for yourself just to make sure that everything's okay. So you can show here that the sine of an angle x is going to be the cosine of 90 minus x here. So in this situation, if x is an angle, right, then you can look at its complement, 90 minus x, and be fine with it. Similarly, the cosine of x here is going to be the sine of 90 minus x. Okay? Now, this actually tells you a couple things about what's going on here. If you look at this situation here, right, notice how in this case here we have this here is sine, and this here is cosine. Note that they represent exactly the same thing here. You have sine and we have cosine. The only difference is this co here. The reason it's called cosine, if you think about this, ladies and gentlemen, is actually cosine is just a shorthand way to say the sine of the complementary angle. So the sine So this in this situation here, the sine of x is equal to cosine of the complementary angle. Or if we look down here, the sine. So in this case, the cosine of the angle here. In this case, the sine of the complementary angle. That's where it comes up here. So here in this cosine here, you can think of this as sine of the complement. So you kind of have this sort of linking here between these two things. You have the sine of the complementary angle here. So you can talk about this sort of thing. So you have this sort of identity here. Both these things here both work out. I call this an identity because this is a statement that is true no matter what value of x you plug in here, so long as x is an acute angle. Okay? So there's actually this only scratches the surface of what are known as trigonometric identity statements that are always true in trigonometry here. You'll be exploring a lot more of these in Algebra 2 Honors next year. But for now, let's just focus on this here. Okay? Now, by now you probably have watched the videos and you probably understand here, have seen the definitions of the trigonometric ratios. And you kind of see where they came from here, but how are they useful? So one of the biggest things about the trigonometric ratios is that we've developed them as a method to find the lengths or find measures of objects that we cannot directly measure ourselves. Most of the time, if we want to learn about an object, how big something is, we would go up to it and measure it ourselves. So, for instance, the table that I'm doing this on here, the length of the phone that I'm using as my camera, how far is it from here to the pharmacy? We can measure those distances directly. But there are specific things here for which we cannot measure them directly because either it's inconvenient for us or it's practically impossible for us here. As an example, let's consider the following here. Now, I get this. Obviously, I'm going to be using a picture here because we're not actually at the actual thing, unless this is on the internet. So it is very possible that some of you are watching from Dubai. So in this case, this is in your backyard. But for most of us, we're not in Dubai here. So, for those of you who do not know, this is the Burj Khalifa. This is currently the tallest building in the world. How tall is it? Well, that's difficult to calculate. That's difficult to actually measure here. So, one thing that we can do here is we can try to measure the height of this object using a different method here. So, you can see the sort of setup I created over here. We can create a right triangle like so. So notice that we have some points. We have our point A here, we have our point B, which is the base of the tower here, and we have point C, which is the very, very top of the tower, like this, okay? And you can see there's actually one of my assistants over here, I think his name is Bob. Hi, Bob. I hope Bob's waving at you. He's kind of tiny, but he's waving at you. Bob has measured some things for me here, and he has noted that this distance from where he's standing to the base of the tower is 4,192 feet. And when he looks at the top of the tower, he finds that he makes a 33-degree angle. His eyesight is 33 degrees to the top of the tower here. Okay, now we're not exactly sure what to do about this, but this is good information here. So in this case here, let's call the height of the building here H, like this. Okay, so I'm going to call that the height of the Burj Khalifa H. I don't know what it is, but I can try to calculate it. So in this situation here, we know that this is a right triangle, or rather we're assuming this is a right triangle, because if this tower is not perpendicular to the ground, we have a bit of an issue here. So we're going to have to be kind of careful about that. But luckily, this is going to be the case in much of current engineering theory. So there's a right triangle here. Now, the goal is to determine the value of the h. So that means in this situation, the only thing that we know is this angle here. We have a 90-degree angle. We have some things. So it looks like we're going to use some trigonometry. And that seems pretty fair. Now, in this situation here, now we have three trigonometric ratios, sine, cosine, and tangent, to marshal here. So we had to pick the one that seems to be the most useful. So it seems to be the case that tangent works the best here, right? Now, you can try using sine or cosine, but if you think about it, sine and cosine both involve a hypotenuse, which means we need to know the length of AC, and we don't know that. So we can use tangent here to write this out. So in this triangle, I can say that the tangent of this angle, tangent of A, in this case, is BC over AB here, right? Because this is opposite over adjacent here, okay? So let's go ahead and actually write this one out here. So now I can substitute the pieces in. So this is tangent of 33 degrees equals BC, which is the height, H, divided by 4,192. Okay, so now I have an equation here, ladies and gentlemen, and just like any other equation, we can solve for this equation, solve for the variable here, H. In this case, I'm going to multiply both sides by 4,192 to get rid of the denominator over here. And we get that the height is 4,192 times the tangent of 33 degrees. So this number here is the height of the building. You'll note that this is actually a number here. Tangent 33 is a number, much like pi or radical 2 or 15. It's a number here. It has a value. Unfortunately, because this number is, has a function embedded into it, doesn't help us out that much because not many of us know what tangent 33 is on top of our heads. So this is what is known as the exact height of the building. So this tells you exactly the height of the building here, but this number doesn't help us out much. What we can do is we can try to figure out approximately what that is here. And that's where the calculator comes in. So the nice part about this sort of thing here is that with your trigonometry, you can actually do a lot of the setup first and then actually take out the calculation device at the very end to put this in. So when you use your calculation device here, you want to make sure that you have that set up. Most scientific calculators or graphing calculators should be able to do this here. So you can enter 4,192 times the tangent of 33. So I'm going to use my calculator over here. As you can see, here's my calculator. I'm going to be using that. And you'll find that the calculation tells you that this is approximately 2,722.3166 feet. Now, of course, we can round this here. We're going to round it to approximately the nearest whole integer, which is 2,722 feet. And that tells us here that the height of the tower to the nearest foot is 2,722 feet. Now, for your calculator here, make sure that you end up with a number that looks like this here. If you end up with a different number, it's very possible that you may have made a mistake in your typing or you ended up in the wrong mode. If either of those things pop up, that's perfectly fine. We can talk about that in the live class. But in this situation here, this is basically how you can use trigonometry to determine missing lengths of any sides of a right triangle here.